have anything that you don't want to be recorded for any reason, just to let you know this class will be recorded. So let us get started with our last lesson of chapter 17, talking about sound waves. Oh man, the physics of hearing. So what we're dealing with here is standing waves again, and we're looking at resonators, open pipe and closed pipe resonators. This is a closed pipe resonator. A closed pipe resonator. So for a closed pipe resonator, you can see one end would be a node and the other end is an antinode. So you want to have your antinode at the end of the pipe. That's how the sound is produced. So when we go through this, remember your first harmonic, n equals 1, that is your fundamental frequency. And then your first overtone is your next harmonic. Now in a closed pipe resonator, your next harmonic is n equals 3. We go by odd numbers here. So in a closed pipe resonator, every harmonic is an odd number. So just to let you know that in a closed pipe resonator, when the resonant tube is closed at one end, we go by the odd harmonics. And that has to do with how the standing waves are created and set up. So F3 is the first overtone, where N is your harmonic. So F3 would be 3 in that case. So just to let you know that as we go through this example problem. All right, so let's go to the next page if it'll let me. Swipe. Do it by hand. What length should a tube closed at one end have on a day when the air temperature is 22 degrees Celsius if its fundamental frequency is to be 128 hertz? What is the frequency of its fourth overtone? So let's do part A first. Fundamental frequency, that means n equals 1. We know the frequency at n equals 1 is 128 hertz. We know the air temperature is 22 degrees Celsius. And we're looking for the length. So for a closed pipe resonator, Fn equals NVW over 4L. F of 1 equals 1. Well, we need the velocity of sound. Remember the velocity of sound formula? 331 plus 0.6 times temperature Celsius. So we got 344.2 meters per second. So we have 1 times 344.2 over 4 times L. L is our goal. So L equals 1 times 344.2 over 4 times 128. 0.672. So that's part A. Part B says what's its frequency of its fourth overtone. So in part B, what is n equal to if it's the fourth overtone if we're going by odds? So 1, 3, 5, 7, 9. So this is our 1 is our fundamental frequency. 3 is the first overtone, 5 second, 7's third, 9's the fourth overtone. So n equals 9 in part B. So it's saying what's the frequency of the ninth harmonic? F9 equals 9 times 344.2 over 4 times 0.672. 1152 hertz. That's how we solve that problem out. Does anybody need anything clarified there? Anybody? All right, let's try another one then.
Wait, I'm sorry. Could you go back?
Sure.
Thank you.
And the n equals 9 comes from where?
What's that?
The n equals 9. Where does that come from?
Because it says it's the fourth overtone. So this is the first overtone. This would be the second overtone. That's the third overtone. That's the fourth overtone. This is our fundamental
Okay.
here.
All right, cool.
Okay, thank you.
Anybody else? All right. Another type is an open pipe resonator. Like a organ pipe or a flute or an oboe. Just a couple examples for you. Now for this one, our first overtone you can see is, this would be n equals 1. It's just regular. So we would have 1, 2, 3 here. Here we'd have 2, right? If we add up our waves, we have 2 waves. So anyway, for closed pipe resonators, we use, or excuse me, open pipe resonators, we use this formula. So when you're doing your test, you just have to remember the difference between the open and the closed, just the 4L and the 2L and the harmonics. So in this case, our first overtone would be 2, our second overtone, right, would be 3, and down on the line. So let's take a look at one of these. What's the fundamental frequency? So that means n equals 1. The length is the same as the last problem. It's open at both ends. That's key. On a day when the speed of sound is 344 meters per second. So it's pretty much the same stuff as the last problem, same information. And it says, what is the fundamental frequency? And then the frequency of the second harmonic. So Fn equals NVW over 2L. 1 times 344 over 0.67. That's not the way you write 67. 2 times 0.672. (256 hertz). That's our fundamental frequency. So then the second frequency, F2, right, for this one, n equals 2. So it'd be 2 times 344 over 2 times 0.672, or 2 times 256, right? They're in multiples, integer multiples, 512 hertz. Those would be your two answers there. Anybody have any questions on that one?
So for its second harmonic, it wouldn't be 3, it would be 2.
Right. It's the first overtone, because for a closed pipe, you go every one for the harmonics, right?
Yeah. Okay.
This is the overtones up here. The third harmonic is the second overtone.
Oh, got it. Okay.
All right, so that's the end of standing waves. The next thing we're going to look at is the Doppler effect. So the Doppler effect is a change in frequency due to the motion of the source or the observer. That's what the Doppler effect is. Change in frequency due to the motion of the source or the observer. So let's just take a look at this. So here's a car putting out some sound at a regular interval. You can see they're arriving at the girl and the boy at the same interval because the car is at rest. So the velocity of the source equals 0. Now, when the car starts moving, the velocity of the source is to the right. You can see the waves are arriving more frequently here and less frequently here. So the observed frequency goes up at point Y, and the observed frequency goes down at point X because it's arriving less. See how it's arriving less frequently, the wave fronts? See how further spaced apart they are? And over here, you can see they're arriving more frequently. And this is why when an ambulance comes up on you in your car, you hear it at a much higher frequency because it's pushing those waves as it's coming towards you. Now, if the velocity of the source is 0, but the velocity of the objects are moving, you can see here, he's getting further and further away from the wave fronts. So his observed frequency goes down. She's getting closer, so her frequency observed goes up. It seems like they're moving closer to her. Now, obviously, you'd have to be going pretty fast to observe this if you were running. You'd have to run pretty fast, but normally it's when something's coming up on you. And the formula to find this out is here. The frequency observed is equal to the velocity of sound plus or minus the velocity of the object over the velocity of sound minus or plus the velocity of the source times the frequency of the source. Now, some things to note down here. Notice how I wrote the plus minus signs. They go together. When the numerator is a plus sign up top, it goes with this. And the minus is away from the source. So if it's a denominator is a minus side, it's towards. And if it's a plus, it's away. So they go together, the plus and the minus signs that I've written here. When it's moving towards, you're going to have a bigger numerator and a smaller denominator. That makes a larger number observed. If you have a smaller numerator and a bigger denominator, that's going to make a smaller observed frequency. Does that make sense?
Yeah.
Kind of. So you have to know when you're doing the problem whether to use plus or minus on the top or the bottom. And this is your rule down here to tell you at the bottom. So these are your two rules. So let's try a couple of these. While standing at a railroad crossing, you hear a train horn. The frequency of the horn is 400 hertz. So that's the source frequency. The train is traveling at 90 kilometers per hour. So that's the velocity of the source. That's 25 meters per second. And the air temperature is 25 degrees Celsius. We want to know in part A, the train is approaching. And part B, It's receding or passing, whatever you want to call it. So we're looking for FS for both of them. Now the velocity of the wave is 331 plus 0.6 TC. 331 plus 0.6 times 25. So the velocity of the wave is, not that, 346. And we know that we are standing. So that means the velocity of the observer is 0. The velocity of the observer is not moving. So if we go back to our formula, when approaching, you have a plus on the top, negative on the bottom, right? Plus on the top, negative on the bottom. Our observed frequency is 346 plus 0 over 346 minus 25 times 400. .08. .15. I don't know why I did that again. Made that mistake there. Oh no. Come on. 431.15 is the correct answer. .15. You guys try part B, receding. So to do receding, we switch the signs up. -0 over 346 plus 25 times 400. $373.05. Boom. Any questions there?
How did you get that out of that equation? Is that what that sums up to? I guess I got 10,000 for some reason.
Yeah, you probably put it in your calculator wrong. You probably took 346 divided by 346 plus 25, which would be 26 plus, which ends up being 26 times 400, which would give you 10,000.
Yep, that's exactly what I did.
So you got to make sure the bottom is in the denominator, is in a bracket.
Okay.
Anybody else? All right. Now we have a source moving and a observer moving in this one. You don't have to include the sign. One's going east, one's going west because they're moving towards each other. It'll take care of itself in the equation. So it says you are driving at 25 miles per hour, meters per second east when you notice an ambulance traveling west towards you at 35 meters per second. The sound you detect from the sirens has a frequency of 300 hertz. Is the true frequency greater, less, or the same as 300? Well, if you're moving towards each other and you hear 300, that means the siren's frequency has to be less. So let's write down our variables. So the frequency of the velocity, let's go a different color, better luck. The velocity of the observer is 25. The velocity of the source is 35. The sound you detect, that's the observed frequency, is 300 hertz. We want to find the frequency of the source. It says assume normal room temperatures. That means TC equals 20 degrees Celsius. So the velocity of sound is 343 meters per second. Whenever you see assume normal room temperature, that's 20 degrees Celsius. Just if, yeah, I think I mentioned that earlier this year, but I'll reinforce that. So our formula, they're moving towards each other. So the frequency observed equals VW plus VO over VW minus VS times FS. Our goal is FS. So we're going to have to cross multiply. So we'll pretend this is over 1. So what's on top goes to the bottom. What's on bottom goes to the top. So that gives us FO times VW minus VS over VW plus VO times FS equals FS. Does everybody see that algebra? So it gives me 300 times 343 minus 35 over 343 plus 25. FS is 251.09 hertz. That couldn't look any sloppier. See how I did that?
Yeah.
Anybody need anything clarified there?
How'd you get the VW? That was the
That's the velocity of sound. So that's the 331 plus 0.6 times 20,
oh, okay.
which is 343. That's just That's the velocity of sound at normal room temperature is 343. It's kind of like a known quantity, you know what I mean? It's like the speed of light in a vacuum, but for sound and air. Anybody need anything else clarified? I was thinking maybe we would take the quiz off since it's the last lecture of the year. Just take a break. What do you think?
Sounds
I'm good
good.
with that.
Yep.
Anybody dying to
Sounds
take the quiz?
marvelous.
What's
Extra
that?
credit?
Come on, Noah. I know that was you.
No, we're being recorded. Be quiet.
Got the
Yeah,
shout
we're being
out.
recorded, Noah. All right, well, everybody, that is it then for physics.